Okay, let's imagine that we've launched a firework straight up into the air and it explodes at height h. And it's exploding at rest. So it reaches its apex and explodes. All the little firework fragments go off in all directions, but they all are launched with the same initial speed. So this V naught is the launch speed of every little fragment. Some are going straight back down, some are going straight back up, all different angles, all different sides. And then all these little fragments fall to the ground, and they all impact the ground. And our question here is, what is the smallest angle that a firework fragment would impact the ground with respect to the ground? Obviously, the smallest angle with respect to the vertical is 0 for the ones that fall straight down. I'm interested in the smallest angle with respect to the horizontal, and that's not necessarily obvious right off the bat. So the first thing we want to do is we want to trace out what the velocity components of these different fragments are as functions of their own launch angles. So I'm imagining there's some angle theta, many different thetas, actually from, well, kind of negative pi over 2 to 3 pi over 2, however you want to say it, pi to 2 pi. Lots of different launch angles, and I want to know what these different angles are when they land. And to do that, I'm going to need to know what the components of the velocities are for these different little bits as a function of position. So let's go ahead and use our kinematics equation that relates velocity. And in particular, we know that the x component of velocity is going to be very easy. That's just going to be v naught cosine of this launch angle theta. That will be conserved throughout the motion. There is no acceleration in the horizontal direction, or we're assuming that. In the vertical direction, though, I'm going to use the kinematic equation that relates vy squared. It'll be v naught y squared plus twice the y acceleration times the difference in position in the y direction. That's just 1d kinematics for constant acceleration. This vy squared is actually not 0. It's something that it hits the ground with, so I'm going to keep that. And then my v naught y, well, that's going to be v naught sine theta, and we're squaring it. My acceleration is negative g. My final landing point is 0, because this is going to hit the ground, but my launch point is h. And notice that'll be that'll be vy squared. Of course, we are looking for the negative value here because these are all going to be hitting the ground moving downwards. And then what we're really interested in here is this angle phi, but of course the tangent of that angle is going to be vy over vx when it hits the ground. Rise over run, I guess you could say. I'm also going to go ahead and put absolute values here because I'm really looking for a positive angle of landing. Of course, really, we should be thinking of this as like a negative, but let's just look for the magnitude. That's fine. So plugging everything in here, what do we get? Well, taking the square root, and I will take the positive square root because I'm looking for a magnitude, we get the square root of v naught squared sine theta squared plus 2gh. Of course, it's greater than you started because you've fallen a great distance. And then we're going to divide by v naught cosine theta, which we got from our no acceleration in the horizontal direction. Let's simplify this a little bit. I'm going to introduce a constant called beta, which will be, what, 2gh over v naught squared. And the reason for this is it's a dimensionless number. It's really kind of the height, at least in some sort of units that we might be interested in. And I want to simplify this if possible. I'm going to bring this denominator into both of these terms. The first term of v naught will become a v naught squared that cancels. Cosine will become a cosine squared. So I'll get a tangent squared of theta for the first term. For the second term, I'll get a 2gh over v naught squared, which is exactly beta, times 1 over cosine squared, which is secant squared. Now I could leave it like this, but it's actually a little more convenient to use our Pythagorean identity on secant squared. Secant squared, of course, is 1 plus tan squared. So when I simplify this down, I'm going to have an extra beta times this. And then I'll end up with a beta on the outside. Now I've only got a single term that's got a theta in it. It'll just be a little more convenient. Okay, so this tells me what the tangent of my landing angle is in terms of the tangent of my launch angle and then how high it exploded. I want to minimize this angle, and because tangent is an increasing function, at least over the domain of interest for us, we're only looking for 0 to 2 pi. Actually, it's actually always increasing, but we're staying away from all the asymptotes. Since tangent is increasing, then maximizing phi is the same thing as maximizing tan phi. And we might as well maximize the square of tan phi, because that'll get rid of the square root, and squaring tangent will also make it maximizing in the region we'll make it increasing in the region that we're interested in, which is from 0 up to pi over 2. So I'm actually going to maximize the quantity tan squared with respect to theta. And I'm going to maximize it by setting this derivative equal to 0. So this is going to be the theta derivative of the square of this, which is 1 plus beta tan squared theta plus beta. Now, of course, beta is a constant here, so that term goes away. 1 plus beta. Derivative of tangent squared will be 2 tan theta, and the derivative of tangent is secant squared theta. Okay, and setting this equal to 0 directly means what? Well, secant squared is never 0, and tangent theta is only equal to 0 when theta equals 0. So that implies that theta is actually 0. And what does that mean conceptually? It means that the angle that's going to be the sort of shallowest angle with the ground are the ones that are coming up directly horizontally from this explosion. Those are the ones that are going to actually end up landing at the sort of minimal angle with the ground. So that's kind of interesting. Now we can plug that back into our original formula, and we see that, sure enough, tan squared of 0 is 0, and so my minimal angle, I'll call it like maybe phi star, put a star on these, is just going to be the square root of beta. There is still a beta left over there. And that means that the angle that is minimal with the ground is going to be the arctangent of the square root of beta, which is the square root of 2gh over v naught squared. If you want to pull the square root out of the denominator and make the square root only a numerator, that's fine too. And there it is. That is actually the smallest possible angle that this makes with the ground. Notice that you really only get 0 if you're on the ground, or if the explosion is incredibly powerful and these all go off at practically infinite speed. Of course, there's a lot of problems with that. But it does only depend on those quantities, and that gives us a pretty nice summary of this result, QED.